Okay, let's start with a bit of a recap from what we were doing last time. If you remember, we had this airfoil and we divided this into 2 degree of freedom system that allows for the heaving motion and for the pitching motion of this airfoil. And if you saw that, we remember that we said there we represented these motions, the pitching with a rotational or torsional spring, and the heaving with a linear spring. We said the stiffness is Kz. We also defined the center of moment, center of mass, the elastic or flexural axis, and the aerodynamic center. And we said the initial angle of attack of this wing is something like theta naught, and it undergoes a pitching of some angle, arbitrary angle, theta. That's kind of where we had defined last time. Further on, we went and we defined our kinetic energy as m into kinetic energy, the spring energy from the torsional and from the linear spring. And we also wrote the generalized forces QZ and Q theta in order to get our Lagrange, get the terms for our Lagrange equations. So far what we have not done is now we probably need to think about how to put all these terms together in order to, let's say, get the terms related to our Lagrange equation. Okay, so let's start by writing one term after the other. So as we saw in our kinetic energy, we have the terms related to z dot and theta dot. We do not have any terms related to z and theta itself. So both these terms go to zeros, right? So dz by dou t by dou z is nothing but dou t by dou theta equal to 0. I'm writing the easiest ones to start with, and then we can write the rest of it. And we can write dou t by dou z as m into z dot plus s theta into theta dot. And similarly, I can write dou t by dou theta dot as I theta into theta dot plus s theta into z dot. And similarly, that implies we can also write the term d by dt of dou t by dou z dot as m into z double dot plus s theta into theta double dot. And similarly, d by dt of dou t by dou theta dot as I theta into theta double dot plus s theta into z double dot. One thing as we can very easily observe, we are saying that m, s theta, I theta, s theta are all the mass or the inertia of the mass, right? And so these are all constants with regard to time, so that they are not changing with time itself, right? So we have all the terms that we need from the kinetic energy part of it. So let's just highlight them, and this term goes to 0. The second set of terms that we have are related to the potential energy or the spring energy that are stored in the spring, right? So the terms related to spring energy, dou u by dou z and dou u by dou theta. So we can write these as kz into z and k theta into theta. So I'm just using the above term that we have for u and taking the derivative with regard to z and with regard to theta. Okay, so now if I put everything back in here, if I start to substituting back, so if you remember, we have this term can be written to be m into z double dot, and this was 0, and this was nothing but kz into z, and this is nothing but minus L. Okay. Similarly, for example, for the next one that we have, we can also write, that here, and we can say that this is nothing but s theta into z double dot 0 and k theta into theta, and this is nothing but L into V. if you put everything back together to write our equation of motion, then we essentially have, just to rewrite everything, m into z double dot plus s theta into theta double dot plus kz into z equal to minus L, and then s theta into theta double dot, into s theta into z double dot plus I theta into theta double dot plus k theta into theta equal to L into E. So these are our nothing but our equations of motion. Okay. So one thing that we probably want to have not yet defined is what is L? What is L or lift? What is lift? L. What is the equation for lift? Right. So we have not yet defined an equation for lift, and because this can depend on, as you have already studied in the course on aerodynamics, this would depend quite a lot on time varying phenomena like gust, and which would also dictate the exact forms for this lift and pitching moments. Okay, so let's start with our first thing we want to do is our lift calculation. So let's try to do our lift calculation. Okay, so under a static condition, we can say that the aerodynamic lift under a static condition I know that I'm writing here. I want you to take the time to think back about what you studied in the course on aerodynamics here. As I write, there's also an opportunity for you to think about it. We can write our aerodynamic lift as L is nothing but Q, which is nothing but our dynamic pressure, times C, which is our chord length, times AW, or lift coefficient, which is nothing but our lift coefficients. We know that we can also write our lift coefficient as AW in times theta naught plus theta. Right? So AW is nothing but the slope of our lift coefficient curve. And this is our effective angle of attack. Right? So we know that our theta naught is our initial angle of attack, and because of this kind of a pitching motion that is there in the airfoil, then there's some additional theta coming in, which is our additional angle of let's say change in the angle of attack that is coming in, which gives us our effective angle of attack in a way. So now if we think about it a little bit, so we can also write our theta, right? So we have, if we think of our airfoil that we had here, so let's redraw our airfoil. So we can say that the velocity is acting in this particular direction. This is the direction of velocity. There's a lift acting in this particular direction, right? Or if I rewrite that, I would say also, like for example, there's a lift acting in here, and there's also along our flexural axis, we have z dot that is acting here. Right. So that's our heaving motion, and there's also velocity of the flow here in this direction, right? Okay. So if I were to write this, so then I effectively have here, okay, so I can write this as like a V, and I can write this as Z dot, which would mean my effective velocity is in some particular direction. So if I know my effective velocity in that particular direction, then that would also mean that I can easily use that to calculate the angle of attack in a way, or effective angle of attack, or theta. So I can write tan theta, right, is nothing but z dot by v. That implies for small angles or small rotations, tan theta is approximately equal to theta, which implies that's equal to z dot over v. So that's, we can rewrite that. So then we can say our effective angle of attack theta naught plus theta is nothing but theta naught plus z dot over v, right? That means we can write our lift coefficient as CL is AW times theta naught plus z dot over v. So there's nothing but our slope of the lift coefficient curve. So this is the initial angle of attack, right? And so we know z dot over v. So that means our lift that we wrote earlier, L, is nothing but Q into C into AW into theta naught plus z dot over v. Right, so if we can easily substitute this back into our equation of motion, so we have the lift. If you remember back again, our generalized forces QZ was nothing but minus L, and Q theta was L into E. E was our eccentricity, or the distance between our aerodynamic center and the flexural axis. I now have calculated what the lift is, so I can put everything back together and write my equation of motion. For a very simple scenario, is nothing but m into z double dot plus s theta into theta double dot plus kz into z, nothing but minus q c aw into theta naught plus z dot by v, right? And similarly we can say s theta into z double dot plus I theta into theta double dot plus k theta into theta is nothing but q c a w into e into theta naught plus z dot over v. So now if we look at it, now both of these the lift here is a function of z dot, which means that the forcing function here, which is the lift, is a function of the motion. So if z dot is changing, that is going to change the force. If the force changes, that is going to change the motion, right? So now we have a force is changing the motion, right? But this change in motion is changing the force, right? So we see that the system is kind of coupled. So as the forcing function changes, that's going to change z dot, and as that changes the z dot, that's going to change the forcing function. Okay, so we'll try to put all of these things together into a matrix form and try to see how we can solve this equation of motion. And what does this equation of motion mean? Okay, now coming back into it, let's start to write this equation of motion. We have already, so this is our original equation of motion that we have. let's say equation of motion. I'm going to try to write this in a matrix form because we are all familiar with this form, right? So we are familiar with this m into, let's say, z double dot plus, or let's call this q double dot plus c into q dot plus k into q equal to whatever, right? So 0, let's say. We are familiar with this particular form from our earlier course in vibration for both free and forced vibration, right? If there was some forcing function, then this will be some F, for example. Some force is acting on the system. With the mass matrix, the damping matrix, the stiffness matrix, the generalized coordinates, and the forcing function, or if it's a free vibration, then it's 0, right? So we are very familiar with this form, and we have already know how to solve this problem if it's in this form. So we will try to separate things out so that we can write it into this particular form. So let's start by saying I'm going to take something out like z double dot and theta double dot, which are my acceleration terms. So if I look at these, we have m, s theta, and I theta. So these are the relevant terms. So I'm going to put them into the matrix form here. So I'm going to say m, s theta, I theta, right? So then I'm going to write z dot and theta dot, right? And if you see, now we can write QCAW over V 0 minus QCAW over V into E into 0. Okay, and then we also have plus KZ, and we have 0 QCAW K theta minus QCAWE over V into Z and theta equal to 0. So that's our equation of motion into a matrix form, right? So I'll leave it to you to look for all these terms once. So we have the z dot here and z dot here. We don't have any terms related to theta dot, so you can see naturally there are zeros. We can take whatever's on RHS to the left hand side, and then our RHS is nothing but zeros. So we have no constant terms, or we have no forcing functions. For example, if we had a gust or any kind of external load, then the RHS is no longer going to be a 0, right? And one thing that you want to see is our damping matrix is not a symmetric matrix, and we'll try to understand the implications of all of these things as we go on. Same thing with our stiffness matrix is no longer a symmetric matrix. We'll try to understand what this means as we go into the next step, right? So one thing that we want to kind of highlight here is that the right hand side is 0, which means that we can easily solve for this problem like a free vibration problem, and try to understand what would happen if some certain things are going to 0, or how things are changing with a particular aspect of it. Okay, so the first thing is that we will try to look at a solution is like if one thing that we have seen here as our damping is a function of Q here. That means, and Q is nothing but a function of our velocity. We already know how to look at this, that our dynamic pressure is a function of our velocity. So that means as Q changes, this would also change the damping itself of the system. So it would also change the stiffness of the system. So for now, let's try to take a very simple scenario. Let's start with a simple scenario where we say Q is equal to 0, right? So this reduces us to a very simple 2-degree of freedom system where we are saying m s theta, I theta into z double dot and theta double dot plus kz 0, k theta 0, z and theta equal to 0. You might ask me what is the value of this thing in a way to write it this way. We will try to see what is the value of writing this. What is it that we can gain from writing it in this particular form? One thing that we remember, if you remember, is that we had assumed that the solution is of the form. So we said the solution is of the form, if you remember from our, we said the solution is of the form z and theta is z theta into exponent of lambda t, where lambda is nothing but our eigenvalue or our natural frequency, right, or natural frequency. Okay, and then we said once we know the solution, we can substitute back into the equation. So we can, if we can substitute back the value for z and theta into the equation, so that we can easily write or rewrite our equations as m into lambda square plus kz and s theta into lambda square, s theta into lambda square, I theta into lambda square plus k theta into z and theta equal to 0 and 0. And from our earlier class, we already remember that for a non-trivial solution to exist, the determinant of this matrix needs to be equal to 0, right? Determinant of m lambda square plus kz s theta into lambda square has to be equal to 0, or otherwise this we get the characteristic equation as mi theta minus s theta square into lambda to the power of 4 plus k theta into m plus kz into I theta into lambda square plus kz into k theta is equal to 0. So we have got a quartic equation or equation with order 4 in lambda. So we have lambda to the power 4. And one thing that we did by assuming that q is equal to 0 was not only eliminate the damping matrix, but we also eliminated some terms which would have had lambda cube and lambda, which would have made it harder to solve this, and analyze this. We primarily want to analyze this and see what the solution holds true. So if we just write this as a quadratic equation, so we can write the solution for lambda as minus k theta into m and plus kz into I theta plus or minus square root of k theta into m plus kz into I theta whole square minus 4 into kz k theta into m I theta minus s theta square. So this entire thing is under the square root, right? So this entire thing is under the square root, whole divided by, right? Okay, so I think I'll probably have to move this thing a bit. Divided by 2 into m I theta minus s theta square, right? So this equation itself is not really giving us any information in that. So we did calculate some kind of a eigenvalue of the solution to it, but we want to understand the behavior of this lambda itself. So what is the behavior? Let's write this down. So our big question is, what is the behavior of lambda? right? So if lambda greater than 0, or is lambda less than 0, right? So we know one thing that we know is all the quantities k theta, m, kz, s theta are all greater than 0. We know all these terms that make up this equation or solution to lambda is greater than 0 individually, but this doesn't tell us if lambda itself is greater than 0 or less than 0. So what we will try to do is, let's try to look at the numerator and denominator separately. So once we understand, we are trying to do this so that we get a feeling of what this lambda is about, how it is changing, and that will give us more information of what we want to look at. Okay, so let's try to start one step at a time and try to look at this. So let's start with the denominator, right? Starting with the denominator. So let's say we have m into I theta minus s theta square. That's our denominator, right? So our goal is to say, is this positive, greater than 0, or less than 0? If we know the value, then what if the numerator is greater than 0 or less than 0? And if denominator is greater than 0 or less than 0, then we can say if it's both are positive, then lambda is positive. If both are negative, lambda is negative. If one is positive and one is negative, the denominator or numerator, then lambda is going to be less than 0. So this is the simple conclusion that we want to come to. Like say, is it greater than 0 or is it less than 0? As we go to the next step, we'll try to understand why we want to know if it is greater than or less than 0. Let's try to think of this as like we're trying to do some kind of a treasure hunt. Okay, so we know that if we go back to our picture of our airfoil that we had at the start of the class. Let's go back to that for a moment. If we go back here, so we have defined b into xa, and we said that our s theta is nothing but mass times this distance about the flexural axis. So we have the center of mass, and we have the where we have the distance from the flexural axis to the center of mass to be given by b into xa. Right, so if we go back, so then we can rewrite our s into theta. Sorry, okay, let's s into theta is nothing but our m into b into xa, and then we can write the I into theta is nothing but I about the center of mass plus m into b into xa whole square. Because I theta, we are looking at for I theta about the flexural axis, right? So we know that the moment of inertia about the center of mass, and using our parallel axis theorem that we have learned in our earlier classes, we can write what is the moment of inertia about any other axis if we know about this axis of the center of mass, right? So this is nothing but the moment of inertia about center of mass. So moment of inertia about center of mass, right? So which means now if we put everything back together, then that we have here, so we have m into m square into b xa whole square plus I into cm, or let me rewrite this here. So this implies I have m square into bxa square plus I into cm, right, into mass minus m square into bxa whole square, which means if I take both of these out, cancel this, I am left out with m into I cm, and this is greater than 0. right? So mass is greater than 0. The moment of inertia about the center of mass is greater than 0. That means that the term itself, the denominator itself, is greater than 0, right? So first thing that we saw, now we know that the denominator is greater than 0. So now that we know that m theta, so then let's go back to the numerator here. Going to the numerator, right? So let's try to copy paste the numerator here so that it saves us time from writing. So let me just copy paste that. Copy. Right? So that's my numerator. I know that this term is greater than 0 here. So this term, as we mi theta into s theta square, we already just found out that's also our denominator. We said that that is greater than 0. So that means this term is greater than 0. This is a squared term, so this should be greater than 0, right? And this term is the same as this term here. So these and this are the same, right? So that means we can easily say that the term inside the square root is always going to be smaller than the term outside the square root, right? So because if you think about it, so we have a square term, and let's say, for example, let's say we are saying k theta into m plus kz into I theta is always greater than square root of k theta into m plus kz into I theta whole square, right, minus 4 kz k theta into m I theta minus s theta square. So the term inside the square root is smaller than the term outside, primarily because we have one positive number, the square of that number subtracted by another positive number. So that should always be less than that, right? So now, but then the one question that we have not thought about yet is that what if this is less than 0? Can this be less than 0? Less than 0. If that is less than 0, then we have something square root of some minus or negative number. Then that would be that would lead to a complex number in there. So now our question that comes out is, right, so if k theta into m plus kz into I theta whole square minus 4 kz k theta into m I theta minus s theta square is less than 0, right? So if this is the case, then that would imply that lambda is imaginary. Remember that this was below the square root, which means that square root of a negative number will lead to imaginary situation. We don't know that yet. We want to prove if this could be the case. If this is the case, then this is what's going to happen. So we don't know. Let's try to expand and rewrite, right? So let's expand and rewrite the above term. Right? So then we can say k theta square m square plus kz square I theta square plus 2k theta kz I theta into m, right, minus 4 k theta kz I theta into m plus 4 kz k theta s theta square, right? So that's what we are going to get. So that means if I rewrite this, if I just regroup everything and rewrite this, so I can get this, I have this term 1, 2 and 3. I'm going to rewrite that. I can write this as k theta into m minus kz into I theta whole square plus 4 kz k theta s theta square. Each of these terms, so this term is greater than 0, this term is greater than 0, that means the overall term has to be greater than 0, right? So that means that whatever is inside the square root is always positive. So thing that we have concluded now, let's rewrite all the entire term for now once, so that we can rewrite everything and have a look at it. Let's copy. So root lambda, say, let's write this big, paste, right? Theta square, right? So now we can say, let's try to separate this all out, whole divided by right, divided by our numerator, denominator is nothing but m into I theta minus s theta square, right? I think that's a 2 as well. Okay, so let's look at each of these terms. So we know that the term inside this is always greater than 0, inside the square root is greater than 0, right? Okay, and then the term outside is always greater than the term inside. Let's say if I call this as term t1 plus or minus t1 plus or minus t2, I can say that minus t1 plus or minus square root of t2, right? So then I know that minus t1 is always greater than t2. So I know that t1 is always greater than t2, right? So we know that t1 is always greater than t2, right? And we also know that our denominator is positive. So we know that this is greater than 0. That means, sorry, this was lambda square. That means we have the numerator is always greater than 0. Numerator is always less than 0. Denominator is always greater than 0. Which implies lambda square is always less than 0. Which implies lambda is imaginary. Right? So we'll try to look at the implications of this as we go ahead. For now, this is a very puzzling result for some of you, but let's try to shed more light on this as we go ahead. What we have done here is just some math. We try to rearrange things. We wrote all we did was we wrote our equation of motion into a matrix form. We wrote a characteristic equation. We got an equation or solution for our lambda or our natural frequency. What we were trying to find here is what is the sign of this lambda square. Is lambda square greater than 0 or less than 0? If it is greater than 0, then it is always going to, lambda is always can be positive or negative. But if it is less than 0, then lambda would always be imaginary. So we try to separate the terms in the numerator and the denominator in order to see if then we saw the denominator always greater than 0. Then we looked at the terms in the numerator to find out if there's a square root, can this term inside the square root be less than 0? If it was, then it would be imaginary. We found that it is not the case, it's always greater than 0. Then we said, okay, the term on the numerator is always going to be less than 0 itself. Right? So that means that eventually now we have lambda square is some negative number divided by some positive number. Which means that the square root of this negative number will always be an imaginary number. We'll try to understand the implications of this on aeroelasticity as we go into the next section. Okay, so now we have our, if you remember, our homogeneous solution. If you remember, we said that our solution z is of the form z exponent of lambda t. Right? If our lambda was imaginary, if lambda is imaginary, as we saw, if lambda is imaginary, then I can write lambda is equal to some a plus I into b. I don't know what this a and b are, but I'm just assuming without loss of any generality, I can write lambda equal to a plus I into b, right? So if I substitute them back here, I can write z, that implies z is nothing but z into exponent of a plus I into b into t. Or I can just separate this out to write this as z into exponent of a into t into exponent of I b into t. Now think about it once. Exponent is something that's going to increase very quickly. So if a was greater than 0, right? So if a is greater than 0, that implies z will explode with time. Right? So b represents our frequency, but a represents our, like in other words, b represents how fast something is going from positive to negative. But a represents the decay rate. If a is greater than 0, that means that the oscillations will increase, uncontrolled oscillations. If a is less than 0, that means this is going to decay. So the oscillations are going to decay. Right? So this is the very interesting part of it, why we were trying to understand if z lambda is imaginary. If lambda is imaginary, and then we can look at the term a, which would tell us if this is uncontrolled oscillation or if this oscillation will dampen with time. So that kind of gives us an idea when we look at a solution to see if this solution is going to be, let's say, uncontrolled oscillation or if it's going to be dampened oscillation. So second thing that now as we remember, now we said our lambda square is equal to some I into something, some complex number. Right? So we said lambda, lambda is basically, so lambda square is some square root of some negative, no, sorry, okay, my mistake. So we said lambda square is equal to some negative number. Right? And if you remember, on the numerator we had something like some quantity plus or minus another quantity divided by another quantity. Which means lambda square itself can be, lambda square can either be minus, let me call this a, b and c, just without loss of generality. Then they don't correspond to the same a, b, c we were talking earlier, but just some a, b, c. It can be minus a plus b by c, or it can be minus a minus b by c. Right? So that means that lambda can be square root of either minus a plus b by c, or plus or minus this, or plus or minus square root of minus a minus b by c. Which means we have 4 solutions, and one thing that we know that is that this lambda is always imaginary. So I can write my lambda without loss of generality as plus or minus I into omega 1 or plus or minus I into omega 2. Here my omega 1 and omega 2 represents the pitching and the heaving motions. If you remember, we had a 2 degree of freedom system. It was not just pitching anymore, but it was pitching and heaving. It was going up and down and also rotating, and there was a torsional motion, which means that there was some kind of a coupling between them. Right? So it was, so now since the coupling is coming from the inertia, it's called inertial coupling from the mass matrix. If you remember our mass matrix, let's just go back for a second to look at our equation of motion. Right? So our equation of motion, if you look at it, there's a coupling here. So these terms are kind of coupling. Oops, what's happening here? So these terms are coupling. Our equation of motion is being coupled here through the mass matrix. If you look at the stiffness matrix itself, it is an uncoupled matrix. So there's no coupling between z and theta. If z changes, it's not going to affect theta. And if theta changes, it's not going to affect z. But alternatively, for our mass matrix, the z and theta are affected by each other. Or in other words, there's kind of an inertial coupling. If the stiffness matrix was full and there was a coupling from the stiffness matrix, it would be called stiffness matrix. Or in other words, the coupling essentially means that each of these motions, the heaving and the pitching, are affecting each other. So far we assumed a very simple idea that what would happen if the damping matrix go to zero, or the airflow velocity itself zero, like a static situation, how the pitching and the heaving motion change because of that. We wanted to make a simple idea to kind of understand how these things are playing a role. And as we go ahead, we'll try to look at different various scenarios and understand how we can use this equation of motion to see what kind of an oscillation we are going to have. So let's look at another scenario. Let's try to what would happen if the center of mass coincides with the flexural axis. Let's assume hypothesis. Center of mass coincides with flexural axis. If you remember, we said that our s theta is nothing but m into x into b into a. So there's nothing but, x into m into p into x into a. So this was nothing but our distance between our flexural axis and center of mass. So which means if center of mass coincides with our flexural axis, then automatically this term is going to be 0, right? So if it coincides with that, then this is going to be 0. So that means now our system changes. That implies our equation of motion is m in 0, 0 into I theta into z dot double dot theta double dot plus kz k theta z theta 0, 0. As you can see now, there is no coupling between the heaving and the pitching motion. So there is no coupling between heaving and pitching. This is almost impossible. This is almost not possible at all, but just a scenario for us to understand what is the implication of when each of these terms go into 0. So it's not very simple to identify these motions itself. So one of the easiest way is we can solve for the eigenvector. If the magnitude of the eigenvector is greater than the theta, then the motion is predominantly heaving. So for example, if the eigenvector for the z is greater than theta, then mostly you have a heaving motion. If the magnitude of this eigenvector for z is lesser than that of theta, then you pretty much predominantly have a twisting motion. What we are always interested in is to identify what is the dominant mode of vibration and what are the particular magnitudes of these eigenvectors, rather than looking at trying to understand or decouple each of these motions itself. Right? So in the next case, so far we assumed that our velocity, airflow velocity, is 0. So let's try to look at the next scenario to understand what would happen if there's a non-zero airflow velocity. How would that change anything, and how would we look at it from the equation of motion and try to understand that? Okay, so let's so far we have had assumed that our airflow velocity is 0, because we wanted to see how we can use a simple scenario to understand the equation of motion. Our whole goal is not to mathematically derive these complex equations, but to understand the physical implications and what is the meaning that these equations are telling us. Right? So let's try to make it a little more complex. Let's assume that the airflow velocity is non-zero. Right? Q is equal to non-zero. So directly you can observe something. So we assume Q is not equal to 0. First thing is we see that the damping matrix is non-zero. Second thing, we can see that the stiffness is unsymmetric. If you remember, without the q terms, this term was 0. Okay, sorry, so this was 0 and this term was 0. That initially, right? Previously when q was 0. Now that q is there, this stiffness matrix is no longer symmetric, it is unsymmetric. Further, because of the existence of this term, we can see that there's a coupling between the heaving and the pitching motion. So if the pitching motion happens, then that also affects the heaving motion in a way, right? So there's a coupling between these two. So there's a coupling is introduced in the stiffness. Previously, we only had the coupling in the inertia or the mass matrix, but now we also have this coupling in the stiffness matrix. Okay, so let's try without loss of generality, let's assume that our damping is 0, right? So just I want to make my life a little easier. I will just assume this to be 0. Assume. Okay, so why am I assuming this? Because I don't want terms like lambda to the power of 3 lambda in my characteristic equation. If it is not there, then it makes it easier for me to look at it and analyze the scenario. So I just want to make sure that these terms don't exist, right? So there's also stiffness coupling. So let me just try to, there's no loss of generality, let's assume that this damping itself is 0. And let's assume that our solution, as we have already done like several times now, we assume it's in the form of z theta into exponent of lambda into t. Okay, so let's assume that this is the form of our solution. So once we have this, then we can rewrite our equation. So we already know our equation. We can rewrite our characteristic form. I'm not going to write that. I'm going to leave it to you as a homework to think about it. It's not very complicated, but I'm happy to post the solution if somebody wants to have a look at it. I theta into m minus s theta whole square into lambda to the power of 4 plus, let me write this here, plus I theta into kz. So if you remember, just to clarify, even though our damping matrix has gone to 0, our dynamic pressure Q is still not 0, right? So it's still there in the stiffness term. What we are trying to understand here, how is the stiffness coupling affecting it, right? We talked about how the inertial coupling affected the system. We are trying to look at how the stiffness coupling affects the system. So Q is still non-zero. We just assume that the damping is 0 just to make our lives easier to think about it. Okay, so Q is still non-zero there. So plus K theta into M minus Q C A W into s theta into lambda square plus k theta into kz equal to 0. So this is nothing but our characteristic equation. Right. So once we have our characteristic equation, we can solve for our frequencies, we can solve for our lambda or the eigenvalues in there. As we saw earlier, I'm going to leave this as a exercise for you to solve. But as we saw earlier, we can just plot that we get two distinct values of omega. If we plot them, right? So I'm going to plot Q versus omega. We want to see as the speed changes, how is this changing the natural frequency? Right? Or how is this changing anything, right? So it might not be changing anything. So we want to look at that. So, and we want to understand what is this flutter speed, right? So we want to find what is QF or the flutter speed, right? So there's the critical flutter speed. Critical flutter QF, right? So then if we plot out, let's say we initially had two roots, omega 1 and omega 2, as we saw earlier. If there's no damping in the system, as this reaches the flutter speed, it merges into a single point. But then if there was a damping in the system, right, if there was damping in the system, then they come near and then they move far away again. So this is with damping, and this is without damping. Right? So with and without damping, so basically that's how the system would behave. As it reaches the flutter speed, these two frequencies come close to each other into a single point. That's kind of where you can think about as the point at which flutter occurs. As Q increases, and if there's no damping, then these two frequencies will merge. However, if damping is present, then they'll move close and they will move away. So the frequencies at which they merge is known as the flutter speed. So in mathematically, we can say that if lambda, mathematically, if lambda is a plus ib, right? So then the flutter speed is at the point when a is greater than 0. Or we can say that the system is stable, oscillations will decay when a is less than 0, and system is unstable when a is greater than 0. So a is the flutter, a equal to 0 is the flutter boundary. So when a is less than 0, oscillations decay, right, implies system is stable. So when a is less than 0, a is greater than 0, explode, implies system is unstable. And if this a is equal to 0, that's your flutter boundary. Right? So that's a very easy way for you to make a distinction whether we have a flutter and what is the speed at which the flutter would occur. In the next section, we will try to look at a general solution for these flutter characteristics. We have taken a very simple scenario where we said, okay, what if the velocity is 0 or the airflow velocity is 0? What would be the inertial coupling coming in? What if there's there, but then damping is not present? In the next case, we'll try to look at how we would assume if there's a general solution and how do we identify these kind of flutter characteristics. So let's write our general equation of motion as A into some y double dot. So y is some form of our generalized, let's say, or like our degrees of freedom, plus rho VB plus D into y dot plus rho V square C plus E into y equal to 0. So here our A is nothing but our mass inertia matrix. This term is nothing but our aerodynamic damping. Right? So then this is nothing but D is nothing but our structural damping. So E is our structural stiffness. And rho V square C is nothing but our aerodynamic stiffness. Right? So if we can easily assume, as we have done so far, that our y solution is some y naught into exponent of lambda t. Right? So we can assume that the solution is of this particular form. We can also assume that some structural damping, let's say, is D is equal to 0. D equal to 0. So no structural damping. Structural damping is like having like a bumper in a way, right? So that's like a damping effect. As like when you drive a car and you have the dynamics that will, as soon as you go through like a pothole or something, or like a hump in the road, then you would see that the car doesn't just jump around, but then kind of the oscillations are damped, some kind of structural damping, right? So if we substitute for this into our system of equation, and we can rewrite, let's say I'll just multiply everything by A inverse and take it to the right hand side. I can say A inverse into rho V square C plus E into Y minus A inverse into V into, rho into V into B into Y dot, right? So I'm just rewriting my equation, whatever I had so far. I took the everything except the acceleration term, Y double dot, to the right hand side and multiplied everything on the left hand side by A inverse, which is nothing but the inverse of our mass matrix. Earlier in the lectures, we have also seen why we can invert the mass matrix, because it's positive definite, so inverse always exists. So this operation is allowed. So similarly, we can write our y dot. We can write our y dot is nothing but 0 into y plus I into y. I is nothing but our identity matrix here, right? So I is nothing but our identity matrix. Right? So we can just combine these two. We want to rewrite our equations in a form of y and y dot rather than y double dot. So we want to eliminate the y double dot. So if we rewrite all of this equation into a matrix form, we can write y dot and y double dot is nothing but 0 minus A inverse into rho V square C plus E, right? I minus A inverse into rho V B into y and y dot, right? So we can easily substitute y is equal to y naught exponent of lambda t, and so we easily know, we already know, we said that this is equal to y naught exponent of lambda t, which would imply y dot is nothing but y naught lambda exponent of lambda t, and y double dot is y naught lambda square exponent of lambda t. A simple derivative that we all can easily know about. So if we are going to substitute all of this back into our equation of motion, so if we substitute everything back here, then we can rewrite our equation of motion, or our as minus, as minus lambda into I minus A inverse into rho V square C plus E I minus A inverse rho VB minus lambda I, right? Let me just move this here, into y and y dot equal to 0, 0, right? So so let me just move this down here, is nothing but equal to 0, right? So once we know that, then we all can always, as usual, get our characteristic equation in order to, let's say, we can get our from assuming, well, from, or not assuming, by setting the determinant to be 0, we get our characteristic equation as as lambda square into A plus lambda rho into V into B plus rho V square C plus E equal to 0. Or in other words, we can write the solution to this equation of motion as in some form where some lambda j is equal to Cj into omega j plus I into omega j square root of 1 minus theta j square. Right? So as the speed increases, the value of the c and omega will change until flutter occurs. Or we can consider this equation to be of a form. So another simple way to think about this is, let's try to just copy this and try to rewrite this. Just copy. So we just consider this equation. So if we go back here, we can rewrite this in a particular form of b4 lambda to the power of 4 plus b3 lambda cube plus b square, b2 lambda square plus b1 lambda plus b naught equal to 0. Which implies that at flutter speed, the real value of the solution goes to 0, right? So if you remember, at the flutter speed, as we go back here, when the flutter occurs, this lambda is going to be, this real value is going to be 0, right? Tends to 0 at flutter. Since omega itself is not going to 0, that would imply that tends to 0 at flutter. Right? Okay, so that implies now if we have, so we assume that we have this equation, and then we have a, if we have a flutter, then we can say at flutter, we can say lambda is of the form I into omega, right? So now if I substitute for I into omega into this characteristic form, is a form, let's say. Right. So what have we done here? So let's just go take a step back here. We have said, so let's try to move this thing a bit. Okay, so we had this equation, we have derived this equation. This is a very general equation. We can say this is of the form as shown here, right? So let me just rewrite this, lambda to the power of 4. From the above, we can see that lambda cube is 0, lambda square is terms are 0. But in general, we can see that this is the equation of this particular form. So b naught is not 0, b1 is non-zero, b2 and b3 are 0, but b4 is again non-zero. And we know at flutter, the real part of the root lambda of the lambda is 0. We have already shown that if lambda is the form a plus ib, if a is less than 0, that means it is below the flutter speed, where it is a stable oscillation which decays. If a is greater than 0, then it's above the flutter speed, where it's uncontrolled oscillation. If a equal to 0, then that's the point of flutter. Which means that at the point of flutter, lambda is of the form ib or I omega, some I omega, right? Without loss of generality, we can write that it is of the form I into omega. So now once we know that it's of the form I into omega, I can substitute that, or in other words, it's actually of the form plus or minus I omega. So it can be plus I omega or minus I omega. So if I substitute, if we substitute lambda equal to I into omega into the above equation, right, the b4 lambda to the power 4 and so on, then that would imply we get b4 omega to the power of 4 minus b square omega square plus b naught, right, plus I into minus b3 omega cube plus b1 omega equal to 0. So let me just put a box here for now so that we can remember this. Similarly, I can substitute if lambda is minus I omega, right? If it was minus I omega, then I would have b4 lambda omega 4, right, minus b square omega square, b2 omega square, sorry, plus b naught plus I into b3 omega cube minus b1 omega. So it's b1 here, not bi, sorry, equal to 0. So again, we can just put a box here. Let us call the solutions as 1 and 2. If I were to sum up 1 and 2, right? So I have these two equations. I said that we have Flutter. At Flutter, there's only the imaginary part exists. Now this can be plus or minus. So now if I do 1 plus 2, I'm trying to get some general Flutter characteristics here. Then that means b4 omega 4 minus b square, b2 omega square plus b naught equal to 0. And similarly, if I do 1 minus 2, I would get b1 omega minus b3 omega cube equal to 0. Which means that I can say from let's say if we call this 3 and 4, right? So from 4, we can write omega is square root of b1 by b3. Right. Similarly, now if we substitute for omega is b1 by b3 into the equation 3, substituting for omega in 3, we have, right, b4 into b1 by b3 whole square minus b2 into b1 by b3 plus b naught equal to 0. Or in other words, this is known as our Flutter condition. Right? So it's our Flutter condition. Just to think about this, what have we done here? So if we have said that if we have a characteristic equation, let's say we have our equation of motion, we can write the characteristic equation. Then based on the coefficients of this equation of motion, this coefficients of this characteristic equation, we can find the condition for Flutter. Or in other words, we can also find the Flutter frequency at the frequency at which Flutter would occur. This is the most important thing for us, is not to identify when would Flutter occur, at what frequency would Flutter occur. For example, it can happen that these b1, b2, b3 coefficients, as we saw, could be function of q, which is our dynamic pressure, which depends on the velocity. And in such a case, we can get an equation for the Flutter, or a condition for Flutter, as to at what velocity would this Flutter occur. Another approach that you can always do is, as we saw earlier, is to look at the Routh-Hurwitz stability criteria that we have already done earlier. One of the things that we have done so far is we assume that there's no gust or any kind of unsteady aerodynamics that is coming into picture. Once we have these kind of unsteady aerodynamics, then we also need to consider other complications that come in the lift calculations. In the next section, we'll try to take some simple problems and solve them to see how we can use the concepts that we have derived so far to understand other aspects of how to determine the Flutter, what is the Flutter condition, and the Flutter frequencies. So far, we have looked at the general equation of motion, and we have tried to understand what would happen if this equation of motion has the stiffness, the mass matrix, and the damping, And how can we get the characteristic equation? And using our characteristic equation to determine what would be the critical flutter speed and the flutter frequency. Let us try to take a simple problem, try to illustrate what we have done so far. I have already directly written down the consolidated form, like the mass and the stiffness and the damping. I have separated all of them out and already so assumed that our generalized solution, let's say our Q1 and Q2, are already equal to some form of, let's say Z1 and Z2 are equal to some form of Q1 and Q2 into exponent of lambda t. We already have done this. We have taken that and substituted us into the equation of motion for the system, and we have some let's say any matrix equation, and we want to determine as usual the flutter speed, the critical flutter speed and the flutter frequency, right? So I would not go into the all the derivations. I will leave it to you, but I would give you some of the final solutions here. If I am writing the characteristic equation, I can take the determinant equal to 0 condition. That would give me the characteristic equation. From the characteristic equation, I can determine each of these coefficients B4, then B3, right, and B2, B1, and B0. Have each of these system, and then we can substitute them for the condition of flutter that we have derived in the previous section when we discussed that. Once we substitute and solve for it, we are able to get two of these speed, which are our critical flutter speeds. And similarly, we can get the flutter frequencies as well. So this is a very simple way, once you know the equation of motion for the system, a simple way to calculate what would be the flutter speed, critical flutter speed, and the corresponding flutter frequencies. So overall, just to summarize everything that we have done so far, we started out assuming that we have an airfoil which is undergoing a heaving and a pitching motion. We said heaving motion is up and down, pitching motion is rotating side, twisting motion. We thought of this as a 2 degree of freedom system in order to derive our equation of motion. And then we said, okay, what if we have a general equation of motion? How would we look at it? Using the simple airfoil, we try to understand what would happen. What is this flutter, right? So when does this flutter occur? What is the physical intuition for this flutter? And what is the mathematical way of finding out if a system is undergoing flutter? Or when does it undergo flutter? Then we took the general equation of motion, which could be for a complicated system, and tried to find a condition of how to determine when this flutter occurs, and a condition for the flutter to occur, and way to calculate the flutter frequencies. Thank you very much. I hope you enjoyed the lecture.